Hello, everybody. Have a great Friday afternoon. It's my distinct pleasure to introduce Professor Brad Holschuh from the Department of Design, Housing and Apparel. He's an associate professor. The Design, Housing and Apparel is part of the College of Design, but Brad has been with MinDrive and MinDrive for a number of years. He co-directs a laboratory for wearable technology in the College of Design. She's going to present a very interesting talk. I don't know if it's going to be as interesting as the one last year with the shark costume, but as we discussed, we're very excited to have him with us. Without further ado, Brad, the podium is yours.
Thank you, Nikos. And I would say it's debatable if my talk is more or less interesting if I'm wearing a shark costume, but next year we'll have to reconvene on Halloween.
Yep.
Good. Okay, let me pull up my slides. Thank you for the introduction. And I'm excited to come and speak to you folks. As Nikos mentioned, I'm an associate professor in the College of Design. But as you'll hear on my next slide, I'm an engineer by training. And so I exist here at the University of Minnesota in kind of an interesting capacity where I'm housed administratively and I interfaced most closely with design students. But all of my background is in engineering, and the problems that I'm really interested in are crossovers between engineering and design. And in particular, I study wearable technology, and I do it in a home program of apparel design. So immediately that should stand out to you as an unusual place to think about engineering of wearable systems, right? We are in a department that is design oriented, and my official title is an associate professor of apparel design. But I consider myself a roboticist, and a soft roboticist at that. And so what I get to spend my time thinking about, and what I'm really passionate about, is trying to create soft robotic systems that are functional, right? That can perform the types of mechanical manipulations that you would expect of a soft robot, but in a wearable form factor that people actually like to wear. And therefore, it is as much an apparel design problem as it is a mechanical engineering or a material science problem. And so what I'm going to talk to you today about are some of these challenges and opportunities and application spaces for wearable soft robotics. And in particular, wearable soft robotics that take textile or garment form factors. Because as you'll hear me talk, there's a really compelling reason for why we want our actuators and our sensors to have form factors that people are comfortable with if we expect them to reliably and happily wear them on their body. So I co-direct a research lab in the College of Design called the Wearable Technology Lab. I'm also the director currently of a graduate program called Human Factors in Ergonomics, which is an interdisciplinary field that studies basically user experience in whatever manifestation that occurs. So it can be users wearing wearable technology, it can be people interacting with websites, it can be people interacting with environments, everything from architecture to writing to psychology to mechanical engineering to apparel design. So I direct that program, and a lot of the work that we do in our lab also is concerned with the user experience of wearing technology. And in my specific case, wearing soft robots. And for that fact, I'm cross-affiliated with MinDrive in the robotics sensors and advanced manufacturing focused area, and I'm an affiliate faculty here in the Robotics Institute. So I wear several hats, and I love all of them. And I think it's by having each of those backgrounds and interest areas that allows me and allows our lab to do some of the cool stuff that you're going to hear about today. So a little bit about our lab. We are just over 10 years old. I think we're in our 12th year this year, founded by a colleague of mine, Dr. Lucy Dunn, in 2009. I joined the university in 2016, so I joined the lab 6 or 7 years into its existence, and I've been co-directing it since then. But Lucy and I together manage this lab space, which is on the St. Paul campus Some of you may have never even been to the St. Paul campus before, but that's where our space is settled, which is where 50% of the College of Design is placed. The other half is in Rapson Hall here on East Bank. But our facilities are quite nice in St. Paul. We have a bit more space over there. So we've got 3 large rooms that are all interconnected, where we host a great amount of equipment, both traditional engineering equipment, but also soft goods manufacturing equipment, because truly we are a crossover lab that does engineering work, does apparel design work, and can manufacture, test, and deploy systems that combine soft fabric materials and engineered components. So we are an interdisciplinary lab. Right now we have 7 grad students working in the lab with us, with 3 undergrads who also participate. And the grad students that we work with come from a variety of programs. We have design students, typically apparel design, but not always. We have human factors students, and we also have engineering students. Right now, we have an electrical engineering student in our lab. We've had mechanical engineering students in the past. We've had biomedical engineering students in the past. And again, it reflects the fact that trying to make wearable systems that are both functional and wearable requires cross-sectional understanding, soft goods, hard goods, user experience, manufacturing. So that's what we do, and it's a lot of fun. The 2 cartoons that you see on the slide here were actually commissioned by NPR. Our lab was featured by NPR a few years ago, thinking about the science of technologies for superheroes. So they created avatars of Lucy and I as superheroes to commemorate that event. But first, if anybody wants more information about what we do, I mean, you can see a lot of the equipment that we sport here, but I really encourage you to go to our lab website, which you see in the bottom right, wtl.umn.edu, which gives a much better overview of many of the projects that we work on, some of which you're going to hear about today. But a little bit of my background. So as I mentioned, I come from an engineering background, and specifically an aerospace engineering background. So being here in the College of Design is a transition from all of my professional training. My bachelor's, master's, and PhD are all in aerospace engineering. And if you're asking how does someone who does aerospace engineering end up as an apparel design professor doing wearable technology, the short answer is there's a small overlap between aerospace engineering and wearable technology, and that overlap is spacesuits. So I spent my graduate career, master's and PhD, working on engineering better spacesuits, and in particular, trying to move us away from the type of spacesuits that you see on the left, which are the traditional inflated gas pressurized garments that you've seen every astronaut ever wear when they're in space. In this case, it's Buzz Aldrin walking on the moon, and trying to move towards a different paradigm for spacesuits that are skin tight. And you see an illustration of what one of those could look like on the right. And the fundamental difference between the 2 of them is that one is inflated and one of them is conformal. The design theory behind each of them is similar. So spacesuits, regardless of type, have many responsibilities when you're in space. And the major one is to keep you alive. So keeping you alive in space is a difficult thing to do because our bodies are not equipped to be in space. And so the 2 most fundamental things that we need replicated on our body when we are in space, in the vacuum of space, is we need something to breathe, oxygen or air, but we also need pressure against our skin. And the gas pressurized spacesuit that you see on the left kills 2 birds with 1 stone. It puts you inside of a garment, which is then inflated, typically with pure oxygen. And then that means that you are in an ambient environment that gives you oxygen to breathe, but also the pressurization of that gas presses against your skin and mimics the pressure that we receive from the weight of the atmosphere here on Earth. The problem with suits that are designed like that, and I'm going to skip forward, is that they're stiff. So here's a video from Apollo 17.
Jack Schmidt having a few problems.
I'm not sure if you could hear the audio. If you could, great. If you couldn't, the commentary here said Jack Schmidt having a few problems, which is an understatement. Jack Schmidt was an Apollo 17 astronaut, went to the moon in 1972, and had a real hard time walking. You see there, he dropped his gear, dropped his bag, and as he bent down to pick it up, the suit was so stiff that it recoiled and it shot him up into the air and it knocked him over. I'll play the video again, and I want you to pay particular attention to his knee joint, because the knee is a really good example of one of the hardest things to design in a spacesuit, which is a joint that allows you to bend it in spite of the fact that it's pressurized. So let's watch it again. Everybody pay attention to his knee.
Jack Schmidt having a few problems.
So what happens there is, as he bends his knee, I mean, the muscles in his leg are strong enough to bend the suit, but in reality, it's the functional equivalent of compressing a spring, right? You are deforming and bending against an interior pressure vessel. And you have enough strength to do that. You can overcome the stiffness to bend it. But as soon as you relax those muscles, it returns to its resting position. It recoils. It's like letting go of a compressed spring, and the energy is released in a mechanical motion that in this case rapidly straightens to the point that it can actually send you up into the air in a low gravity environment, into the lack of air, into the vacuum. And this is true for any spacesuit that's ever been developed, because spacesuits are all, first and foremost, pressurized garments to keep you alive. And as long as you put somebody in a gas pressurized balloon, which is effectively what this is, you are always going to have a stiffness problem. So the work that I did in graduate school, I'm going to go back a slide now, was to think about how you might make a skin tight suit. So a skin tight suit has different design requirements. You would still have a helmet filled with pressurized air or oxygen, because you need something to breathe, and there's no two ways around that. But your body doesn't care how it gets the pressurization over the rest of its surface. It's easy to do it with a pressurized gas, but it doesn't have to be done with a pressurized gas. You could do it with a tight-fitting garment. And lo and behold, in the 70s, someone tried to build one of these. They're called mechanical counterpressure spacesuits, and here is an example of a prototype that was actually built and tested in the early 70s, called the Space Activity Suit. And what it is it's a 7-layer leotard. And each layer of that leotard gets tighter and tighter and tighter and tighter until after 7 layers, it's tight enough so that you can survive in a vacuum.
So
and here's a video of somebody using this suit.
So I call this the second skin.
So this is a case of someone wearing the Space Activity
idea,
suit, doing
maybe a great
actual
idea
physical tasks in a vacuum. They can crawl, they can climb ladders, they can do the types of physical tasks that you would need them to do
mobility, and now you can
when they are in a highly physical activity like doing spacewalking on the moon. The problem with a suit like this is not that it's too stiff. In fact, it's not stiff at all. It's no stiffer than a tight-fitting garment being on your body. The problem is that it's nearly impossible to put on. You can see the final screen from that little video clip is the subject having the suit put on them by 2 assistants. And the reality was, in order to get this suit on your body, it needed to be 7 layers thick, as I mentioned, and it took 45 minutes and 2 assistants to help you get layer by layer by layer on. And that limitation in the operations of the suit were too steep to convince NASA to actually send it to space. And so in the 70s, they didn't send this to space. And today, the astronauts that are going to space still are not wearing suits that look like this, because you have this fundamental problem of a really tight-fitting garment being almost impossible to put on. And to give you a sense of how tight is tight, how tight are we talking with this skin-tight garment, the benchmark for any gas pressurization or skin-tight suit in space in order to keep you alive is 29 kilopascals. And that's not a number that's really easy to understand. It's 225 millimeters of mercury, which is an equivalent pressure rating. But even that's a little bit hard to understand. So to help you put that in context, a medical grade compression sock, like the types of socks that folks with poor circulation wear, those tend to run between 20 and 40 millimeters of mercury. And most folks that have to wear those types of compression socks say they're so tight that they're uncomfortable and they're really difficult to put on. Translate that into the spacesuit requirement here, and remember the number I said, 200 125 millimeters of mercury is how tight the spacesuit needs to fit you. So without exaggerating, this spacesuit needs to be on the order of 10 times tighter than a medical grade compression stocking. And that's the reason why it had to be 7 layers thick. That's the reason why each layer you needed help from 2 people to put on. And that's the reason why NASA has still not sent a suit like this to space, despite the fact that the operational improvement once you're in the suit is obvious, right? You can move much easier in a suit like this than you can in a gas suit. It's just getting over how you don and doff, how you put on and take off a really tight suit is a problem that had yet to be solved. So the work that I did as a grad student, the work that got me into questions of wearable robotics, and work that is still being translated to today, all relate to this challenge of, what if we make a soft suit like this compression suit mechanically active? What if you make the dimensions or the stiffness or the pressures or the forces or any other mechanical property about a wearable garment controllable and dynamic, so that it's not just a passive fabric that you have to struggle to put on, but it is a living, breathing surface that is on your body, but then can react to you. And it may be that it could take a really tight fitting suit and make it loose fitting so you can put it on. It may be that it can take a really loose fitting suit and tighten it around you so that you can receive medical grade compression once you activate it. Or it could mean any other number of things, all of which become possible when the textiles and the clothing that you're wearing now are no longer passive things. They are active, they are controllable, they are responsive, they are robotic by every sense of the definition. So that's what we work on now in our lab. It's this idea of making wearable robots, but doing it not in traditional robotic form factors. So here, are some obvious, some fictitious, some real, but quote unquote traditional styles of robots, and in this case, wearable robots. These are powerful, rigid, pretty bulky, stiff things. They are structures that sit atop your body and then can provide mechanical impetus to you. So they can provide forces, they can generate torques, they can provide bracing or stiffness, right? An exoskeleton is the perfect way to think about what a wearable robot might want to do for you. All of the things that an exoskeleton or an exosuit might want to do. The problem is that rigid, bulky superstructures like this are really, really uncomfortable to wear. Not only are they uncomfortable because they are nothing like clothing, but they are potentially limited in what they can do. Now, functionally, they're powerful, right? The reason why we go for rigid structured design of something like an exoskeleton is that creating and translating mechanical forces is a lot easier to do if you're dealing with a rigid thing, because you can reliably know where the force will translate, what the moment arms will be, etc. Like rigid things are easier to move than soft things because the compliance that comes from a soft thing makes mechanics more difficult or less reliable or harder to repeatably achieve. But the problem, again, is that you don't see people wearing robots like this except out of really niche circumstances now. Yeah, you might find exoskeletons on soldiers. You might find really specifically designed rigid exoskeletons for medical rehabilitation, right? Folks with stroke recovery, folks with mobility disorders. But you don't see these things in everyday life, really rarely, right? You don't see someone at the grocery store wearing something like this. You don't see your grandparents wearing something like this. These are things that are powerful and good at what they do, but not easy to deploy. And often you have to spend a lot of time customizing the fit precisely, and they're heavy, right? They're hard to walk around in. They're hard to do other things with because you now have a giant mechanized rigid robot on you. And so things like this were non-starters for the problem that I preceded this slide with, right? The problem of trying to study the skin-tight spacesuit. There was no room to put a giant rigid superstructure in parallel with the soft spacesuit, because as soon as you start doing that, you eliminate some of the performance benefits that you're hoping for with it being a soft textile. And so when we started that work, and what continues today, is an effort to try to create robotic systems that themselves can be produced in soft form factors, and in particular in form factors that then can be translated easily to something that you would be happy to wear, and that you could wear in uncontrolled circumstances and still receive the functional benefit without the loss of any of the wearability considerations that you demand of the clothing that you're wearing right now. So what you're going to hear me talk about is work toward that effort, and in particular, thinking about categories of materials and architectures of those materials to create soft wearable robots. And in particular, looking at active materials. Active materials are a large, heterogeneous category of any material which itself exhibits actuation ability. And if you want that more precisely defined, these are materials that can be stimulated in some way using some modality, which produce, for our purposes here, a mechanical response. So again, it can be a displacement, it can be a force, it can be a bending motion, it can be a torque, it can be a pressure, right? We're looking for controllability with respect to stimulus and output to create mechanical effects. Now, the reason why active materials are a heterogeneous category is because there are dozens of different materials that might fit those requirements that I just described. And the only common feature between them is a stimulus-output relationship. Within that category, you find everything from metals, like shape memory alloys, to polymers, like shape memory polymers or dielectric elastomers, to fluids, ferroelectric and ferromagnetic fluids, to hybrid solid liquid systems like ionic polymer metal composites. And the list goes on and on. This is just a snapshot of some of them. And each of them, again, offer some form of actuation response behavior, but outside of that, offer wildly different form factors, performance metrics, and controllability realities. Some of which might make sense to put on the body, which is what I really care about. Some of which would be a really terrible idea to put on the body. So we've spent a lot of time playing around with these different categories of active materials, and we found a few different paradigms that have given us a lot of success for creating wearable soft robots. And I'm going to talk about those for the rest of this talk, and we're going to center specifically on the third one in this list, which are called shape memory alloys, SMAs. Shape memory alloys are metals, metal alloys, typically nickel titanium, but not always nickel titanium, which exhibit phase transformations as you increase their temperature. But not just any phase transformation, they exhibit solid to solid phase transformation. So this means that as you heat them up, they begin as a solid in one crystal structure, and as they go through a temperature transition, they transform literally at the crystalline level to an entirely different solid with an entirely different crystal structure. And the process of going through that transformation leads to a mechanical effect, a stiffening effect, or a shape-changing effect that you can then engineer and exploit to use as an actuator. And they can be repeatedly deployed. You heat them up, you cool them down, you heat them up, you cool them down, and you get an actuator out of it. And the great thing about it is that they're commercially available, and you can, after the fact, engineer different forms of actuation behavior into these metals. And so this is what we do in our lab. One of the most common actuator structures that we work with shape memory alloys are springs. Now, springs might seem pretty straightforward. They're centuries or millennia old devices, but when you take the form of a spring, but you create it with some of these exotic materials that can be phase transformed as you heat them up, you then can create a linear actuator that behaves like an artificial muscle. And this is what that actuator cycle looks like. You can take some of this wire, nickel titanium wire, off the shelf, wind it into a really, really tight spring, heat treat it so that that tightened shape of the spring becomes its memory state, And then that becomes the form that the material tries to recover to every time you heat it up thereafter. So we form it and we forge it into a spring. And then we have a linear actuator, which in cold state can be deformed. You can take the spring and you can extend it and it will stay extended. And then when you heat it up, either using direct heating or using joule heating with an applied current, you can create linear actuation. So that spring, which has been overextended, can then recoil and produce a linear displacement or a linear pulling force or a tension or a pressure or whatever it is that you want to generate. And you can wind these springs in really remarkable form factors. We make them where the outer diameter of the spring is about 1 millimeter, but you can wind them smaller or larger than that to alter some of the force properties. And so then these become millimeter scale artificial muscles, which can then be worked into textiles or at the seams of textiles to produce mechanical effects in the garment and therefore on the body of the person who's wearing it. So this is one architecture that you might design using shape memory springs. So it's basically the most simple thing you can imagine. It looks like a tourniquet. You're on the left. Imagine that white cylinder is your arm or your leg. Imagine the green material is just a passive fabric. And then imagine you hook up, in this case, how many? 5 springs to it in parallel. So the 5 of them together act as 5 artificial muscles whose forces add because they're put mechanically in parallel with one another. And then you connect it around a circumference to create a pulling force. And then as the actuators contract, it creates a stress and therefore a strain and an extension in the passive fabric. And ultimately you end up at an equilibrium state where there is a captured tension around the circumference. And if you're trying to, for example, produce compression, which is what we cared about in the spacesuit example, you now have controllable compression. You have, in effect, a tourniquet that you can create varying amounts of squeeze depending on how hot you're willing to get those actuators and how much power you can supply to them. So this is some work that we worked on right at the end of my graduate career, 2015, 2016. And so we built a bunch of these systems, and we also went through the effort to try to analytically model them. Right? We don't have time to go through all the details here, but what you see here is a predictive equation that lets you manipulate a bunch of the system parameters here with respect to the fabric and the actuators and the radius that you're wrapping around, et cetera. And you can model the amount of force and even do optimizations for different design requirements, which is what you see in the 3D plot there, to create different performance metrics for a soft tourniquet or a soft compression garment in this case. And again, I've got slides here. We could go deep in the weeds of the optimization process, which I'm not going to do, but based on different design requirements up to and including that really intense spacesuit requirement, the 225 millimeters of mercury requirement, you can achieve that using a shape memory activated compression strategy. And you can model and estimate the performance using the set of optimization and design parameters. So you're all probably asking, what does this look like in action? Well, here is what a set of these actuators can do. So this is a video. There's, I think, 12 of them run in parallel with each other, hooked up to a power supply. And you apply a current through those actuators, and you see a contraction. Right? That's a linear artificial muscle. And in this case, it wasn't a very large centimeter scale contraction, but doing that paired with a really, really stiff fabric can produce monumentally high pressures without requiring very large displacements. And on this chart, you can see precisely what that looks like. So this is a figure actually pressure sensing of a shape memory activated tourniquet. So on the x-axis is time, the y-axis is the average tourniquet pressure spelled out in kilopascals. So the small red dotted line, which you see right at about 30, that's the spec for the spacesuit. It was 29.6 kilopascals. So that level of counter pressure was the singular performance requirement for my PhD work in this space. And what you can see here, this is one of the figures that actually appeared in my dissertation. We exceeded it. You can see starting at a pressure of about 15 or 16 kilopascals, applying a few step inputs in voltage, you can see the pressure reliably increase And as you increase the voltage, so too does the pressure, because the stiffness of the materials is increasing. And we landed at 34.3 kilopascals. We beat the target by more than 10%. And that, when I got that data, that was when I started celebrating, saying, hooray, they're going to let me graduate. I solved the problem. One of the downsides to these materials, which we'll talk about on the coming slides, is, and I acknowledge this fully, these materials produce actuation as they go through phase transformation. They go through phase transformation when they get hot. Now, hot is a relative term. There's several flavors of these alloys with different material compositions and different temperature transition windows. But when you're dealing with actuators of this form, you have to keep them hot in order to keep them stiff. And as soon as their temperature drops, either because you've turned off the electricity that's heating it or because they've acclimated to ambient temperature, so too will the force and so too will the stiffness drop off. And so in order to achieve pressures like this, they have to be continuously powered, which is not ideal. So the next thing that we started working on was, okay, what happens if we start combining these actuators with some more traditional apparel structures? So what you see in this slide is a picture of something that you're all familiar with. This is your standard buckle, right? On one side, they call it the male side of the buckle. You have the tab that sticks up. It inserts into the other half of the buckle. And once that tab crosses a threshold, it's mechanically captured. What if you took a standard buckle like we've all used on our backpacks or on our coats or on a life jacket and paired them with these actuators? That's what you see on the right. It's the same buckle structure, but superimposed on the top of it are 12 or 14 or 20 parallel artificial muscles. This becomes a really interesting mechanical device because here you can actuate the springs who are strong enough to pull those pieces of the buckle together. But as soon as you reach that engagement point, as soon as the tab crosses the bar that holds it in place, now you have a passively captured mechanical system. And it doesn't matter if you turn off the power because the buckle stays buckled until somebody comes in and manually lets it go. That's really compelling because that eliminates the single biggest frustration with working with temperature sensitive actuators, in that now you don't need continuous power or continuous heat in order to achieve a sustained mechanical effect. You only need temporary heat and temporary power such that you can engage this structure. And once it's engaged, you can turn off the power, you can let it cool down, and you have a compression garment that has buckled itself closed. Think about that. Think about what this means. Any structure, anytime you need to fasten something on your body, a belt, suspenders, your shoes, tight-fitting upper or lower body garments, all you need is one of these structures and a minimal amount of power, and you can take something from loose to tight fitting automatically. You have a robotic buckle is in effect what this is. And it makes me laugh, but we got a patent on this exact device. So it was the first patent that I ever earned in my engineering work, and it's for a robotic belt buckle, effectively. But it's a highly useful thing. Here's a video of this in action. So I haven't started it yet. This is a compression garment that uses 6 of these buckles, each put in parallel. And you see on top of each buckle are a bunch of springs. What this video is going to show you is a compression action where those buckles will pull closed. You see they're only going to move about 1 centimeter in distance. And then the tongues of the buckles are going to engage, right? They'll get caught, and then you can turn off the power, which isn't going to look all that dramatic. But I'm going to tell you right now, the fabric that you see here, that purple fabric, is canvas. Anybody that knows canvas as a material knows that it is one of the stiffest fabrics in existence. If you try to pull on a piece of canvas, it's not going to stretch. It is a woven material designed not to stretch. And with these actuators and with these buckles, we can stretch a piece of canvas over 1 centimeter and then capture it in place. So let's watch. So it's going right now, it's moving quite slowly, but you'll see those structures are pulling closed. And then eventually, if you look down the middle, you see those little tongues of those buckles, one by one, pop out because they've reached the point where they've been mechanically captured. And the exciting thing here is that this structure with that canvas combined with those buckles can produce, again, the target pressure that we care about, the 30 kilopascals that you need to keep somebody alive in space. And this is what the data looks like for that test. I've put little red asterisks on there. Those are the points where the buckles engaged. You saw them in the video. They didn't all happen exactly at once. And here we can actually see in the data points where you reach a stable plateau point when one part of the garment is now mechanically captured and it won't let go. And most compelling is that you see after the 6th asterisk, meaning the last buckle has engaged, we turned off the power and you see very little loss in terms of generated pressure. From that, the black and white dotted line on the right into the future is the unpowered condition, but still producing the powered output, right? Here we want pressure that can be sustained at an incredibly high level, and we've been able to do it by using the actuators to get to that point and using the mechanical buckles to sustain it. So that's sort of the best of both worlds between a soft robotic piece and a traditional apparel piece to give you the outcome that you're looking for this application. Now, this isn't the only actuator structure that we've worked with or that we've optimized in our lab. Another really interesting structure are textiles themselves. So I don't know if any of you have ever taken the time to think about the structure of the textiles that are in the clothing that you're wearing, but textiles are remarkable in their mechanics and in their manufacturing. If you ever thought about having to make a textile from scratch, it's a pretty daunting task to achieve the types of things that you see in your clothes every day. But textiles are structures. They're two-dimensional structures made from one or more one-dimensional-esque materials. If you combine a traditional textile structure with a temperature-responsive material, in this case, a shape memory wire, you can achieve some really exciting two-dimensional actuations. So here is an example of a knit. So a knit is a structure that's made typically from just one fiber looped among itself, row by row by row. So hopefully by looking at the geometry here, you can imagine the path of one SMA wire sort of serpentining and then coming back along itself and serpentining again and going row by row by row and creating those horseshoe loops that you see. And each adjacent row engages with it. So here, we don't even have to go through the effort of making something like a spring to be an actuator. All we have to do is take shape memory wire right off the spool, bought from a commercial supplier, and textile with them. And in this case, create a knit out of it, and you'll see what it can do. So here's a video. This is the knit being heated in an environmental chamber. And the video is kind of choppy, I apologize. But what happens here is a two-dimensional actuation. You can imagine what's happening. That wire, its shape-changing inclination when it comes off the spool is to straighten out. And so because we've forced it into this horseshoe serpentine pattern, which deforms it, then when it heats up, each row tries to pull itself straight. But because the rows are intertwined with one another, it means that each row is trying to pull itself straight and it's antagonizing the row next to it. And so row by row by row by row, there's an effort for the fiber to straighten itself out. And that creates a pulling force in one dimension of the fabric. So again, what you'll see here, I can play it again, is it shrinks up and down in the perspective that we're looking at, but it also expands left and right. So the fabric here being two-dimensional and with the elements being interlocked with one another, you get both a contraction and an expansion, which makes this a different and also interesting actuator structure. But most compelling is that this is an actuator structure that is nothing more than a textile. There's literally nothing else here. There are no motors. There's no even springs. This is a fabric. It's made out of a metal wire, I'll grant you that, but it is a textile. And simply by virtue of heating and cooling that textile, you can create mechanical effects. This is kind of like the holy grail for wearable soft robotics, because our dream in our field is to be able to make clothing and garments which act like clothing, except when you want them to act like a robot. And nothing does that better than a textile. And this is work that's ongoing in our lab. It's a partnership with a professor in mechanical engineering, Professor Juliana Abel, who is an expert in knitted shape memory actuators. So we've got a really great ongoing partnership with our lab and her lab, trying to optimize, but then create systems for wearable robots using these base actuator structures. Okay, so I'm going to quickly go through some current trends outside of my lab that's working in this space to give you kind of a 30,000-foot view of where fiber-based soft robotics stands right now. And then I'm going to talk through some of the applications that we're working on, and then hopefully leave a few minutes for questions. So I'm going to move through these next slides relatively quickly. Okay, so what are other people doing in this space? There's some really awesome work that's being led out of UT Dallas to try to create, again, fiber-based artificial muscles, and you'll see some pretty familiar structures here, springs, most commonly, twisted fibers into springs, but not made from shape memory materials, not made from alloys, I should say. These aren't nickel titanium, these are nylon. Standard, basically fishing line, a polymer that doesn't have anything particularly special about it, when coiled into these structures and then heated and cooled, can produce pulling forces. So there's a really awesome paper from 2014, and there have been some follow-on papers since then, looking at, you can see the name of the paper, published in Science, Artificial Muscles from Fishing Line and Sewing Thread. So when you're talking about wanting to converge on a future where we can create textile-based robotic systems that mimic clothing, the closer that even the fibers themselves can get to natural fibers, or even the types of synthetic fibers that you find in your clothing, the better. You know, nickel titanium is great for what it does, but nobody currently buys clothing made out of nickel titanium. So if we can replicate what I just showed you using nylon, that's an even better future, because that's even closer to the dream of having clothing-based structures that have robotic properties. Other work in this space, this was a paper put out by MIT a bit more recently, also looking at using nylon, but in a different way than the folks at UT are doing it. Here, the MIT folks take nylon fibers and coat parts of the fibers in a conductive material. So now these are electrically conductive nylon fibers. But what's interesting about it is they don't put the conductive material uniformly across it. They put it across pieces of it and then run a current through it. And then those pieces where the conductive films sit get hotter than the places where the conductive film is absent. And by then heterogeneously heating these nylon fibers, you create differential bending, right? The heat of expansion causes parts of the fiber to expand more than others. And that difference in expansion caused by differences in heating lead to actuation. So again, nylon seems like a really compelling backbone material for fiber-based soft robotics. And it seems like temperature is one of the more compelling ways to produce effects, either entirely homogeneous nylon fibers or selectively coated nylon fibers to produce asymmetric bending in the structure. Other interesting approaches to fabric-based soft robotics. This is a group that started at Purdue. It's now based in Yale, looking at robotic fabrics. So here, again, trying to make a fabric with SMA materials in it, a lot like what we do in the Wearable Technology Lab. But instead of putting those fabrics on people to manipulate people, they take these fabrics and they put them on styrofoam or other inanimate but deformable soft objects. And then you now have a totally synthetic robotic structure. So the actuation is happening because the skin is deforming or stiffening or bending, but then it's imposing those loads on the underlying soft structure, which creates useful movements. So again, you can see a bunch of different things that are possible with this approach, trying to make robots, soft robots here that can move or bend or even locomote, because the soft skin is manipulating the soft structure underneath it. I want to point out the work that's being done by Professor Abel's lab here in mechanical engineering. She is a world expert in knitted actuators. And so the base structure that I showed you a few slides back was developed in partnership with her, but she's done a lot of work looking specifically at the 2- and 3-dimensional reactions of knitted structures with shape memory materials as constitutive elements. So not necessarily as fabrics in garments, but as 2-dimensional active skins. So it could be applied to a garment, but it also could be applied to the surface of an aircraft or to plumbing fixtures or to costumes, in anything that you might think about. And the cool thing about her work is that she's done a great job mapping out the relationships between different textile structures and the resulting actuation behavior. And you can see on this slide from a really great paper she published in 2013 of the really elaborate types of 3-dimensional geometries that you can create using a very similar base textile. It's not just contraction. You can get bending, you can get expansions, you can get contortions, you can get out of plane movements. And it's all relatable between the 1-dimensional fiber, the 2-dimensional textile structure, and the resulting 3-dimensional configuration that that structure achieves when it's heated. And then finally, a really great lab working specifically on wearable systems using a variety of soft sensing and actuation structures is the group at Harvard led by Connor Walsh, which is the Harvard Biodesign Lab. And they work on soft exosuits specifically. So they're like us, that they care about wearable technology really strongly, to kind of improve human performance or overcome physical disability, but using soft systems. And they may be shape memory driven, they may be Bowden cable and electromagnetic motor driven, but they try to build in entirely closed loop robotic capabilities. So that includes motion and stress and stretch sensing, which then feeds back to these soft actuators to actually produce closed loop control for some really elaborate soft manipulations of the body. Okay, so let's do a quick fly through of some of the applications in our lab, and then I'll open it up to questions. I see we've got about 11 minutes left till our deadline. So things that we're doing in our lab. Well, first and foremost, we are obviously working on compression garments, right? This was the genesis of my work in wearable soft robotics, and to this day, the work continues. So again, I alluded earlier, folks that wear compression garments for medical conditions universally hate the experience. The 2 types of garments that exist on the market right now to provide compression to a body segment to help with circulation or to help with swelling look like the 2 things you see here. Either they are an elastic garment on the right, or they are an inflatable garment like you see on the left. And the really ironic thing about these 2 designs for everyday compression garments is they mimic both the performance capabilities, but also huge limitations of spacesuits. You can think of the one on the left as the gas-inflated spacesuit. You can think of the one on the right as the skin-tight spacesuit. And the same problems that you see in those spacesuits manifest in these medical devices. The one on the left is inflated, so it's controllable in that sense, but you can't bend it, right? You have those things on your legs, you're going to be sitting down until you're done getting your treatment. And most people, if they need compression therapy, don't want to have to sit all the time. It defeats, the active life that they're trying to gain by getting treatment. The one on the right is bendable, right? This isn't an inflated garment, but everybody hates trying to put them on. They're too tight for you because they squeeze you because they're too tight for you, and they're too tight for you because your body is bigger than the garment, right? They're undersized, and so you get squeezed on your legs intentionally because they are made to be too small for you. But that means that people don't like putting them on. They tend to be really difficult. And when they're on, they tend to be pretty uncomfortable because they're squeezing you all the time. And it might not be the case, medically speaking, that you even need to be squeezed all the time, but this is the best that we can do. And so on the market, millions of people and billions of dollars of product are developed and sold for compression therapy, and everything on the market that does this is bad. So what we're working on in our lab is translating these materials to try to solve some of these medical related compression therapy usability problems. So this is an example of one garment system that we built in partnership with the Mayo Clinic, which uses spring actuators integrated across 4 garments. So you see here 2 garments for the thighs, 2 for the calves, with a bunch of these springs wrapped around in different places. What's really exciting about these types of designs is that each of those springs are an independently addressable robotic actuator. So now you can take something and have it be loose fitting and then selectively tighten different areas of the body if and when you want to. So at a minimum, this can overcome that difficulty of it's too tight and therefore too hard to put on. You can put all these garments on, flip a switch, and it'll tighten around you. And even if that's all it did, it would be better than the stockings that you saw on the previous slide. But we can even do better than that. These are dynamically controllable elements. And so we can create different squeezes at different locations, at different magnitudes, and at different times. So you can create some really elaborate and functionally impossible compression profiles that change with time and with need and with circumstance. And you can't do that with the types of garments that are out there right now. And only by having this be a soft robotic system can you make them spatially and temporally dynamic in that way, while also not having to wear an inflated leg sleeve that forces you to sit down. So we get the best of both worlds there. Similar to it, we think a lot about compression garments, not just for lower body circulation, but for calming and behavioral effects. So many of you are probably familiar with the weighted blanket craze that we sort of are in right now. The idea that compression on the body can actually have a calming influence on your emotional state, right? It can resolve anxiety, it can calm you down, it can intervene if you're having social issues or a panic attack. And again, there are products on the market right now that purport to do this, but they do it badly. You see in the upper left, this is a compression shirt that they give to kids who have sensory processing disorder, but now they have to wear a life jacket like this that squeezes them all the time, whether or not they're having emotional problems. A different product, which scares me that is even existing, is what you see in the bottom left, which is like a Play-Doh rolling device that, again, you can stick somebody in, and those rollers, you can press down on them to give you that haptic stimulation, in theory, to calm you down. I can't think of a worse thing to be placed inside of if you're having a panic attack than a giant Play-Doh roller. But this is a product that's on the market. And so we've had a project with NSF to try to recreate the capability that you get, again, from those lower body dynamic compression garments, but again, as an upper body device that discreetly encloses robotic actuators so that you can create compression on the body for behavioral interventions, but in a form factor that's discrete. Nobody necessarily will know that the jacket that you're wearing has robotic actuators at the seams. And you can interface with it wirelessly, you can flip a switch, you can create a stimulus on a person to calm them down or to make them feel better in ways that are socially discrete, but also dynamic and controllable. So we've built these guys out. This is an example of some of the data of what these garments can generate. This is a paper we published in the Journal of Medical Devices a few years ago. We've also started spinning this out for adults. So it doesn't have to be just for kids. This is an example of an upper body garment that can compress you at the side seams, can compress you at the shoulders, could even have an armband attached to it, again, to give you a calming influence if and when you need it. And we've even taken these garments a step further. Here's an example of a really fleshed out version of this that has actuators on the hands, on the torso, on the shoulders, on the upper arms, to create novel haptic experiences. So a garment like this, you could potentially use to create communication devices. Two people wear these garments. Now you can squeeze each other across distances. Maybe someone's wearing this when they're in a virtual reality environment. Now you have responsive haptics to augment the visual and auditory stimulus that you get from VR. And as an example, what's great about these things is that they're pretty easy to build into a garment, but they are independently accessible. So here is an example. You have 5 actuators. You can activate some of them. You can activate different parts at different times to create different magnitudes and different spatial experiences, because each one of them is an independent addressable actuator. We have projects looking at exoskeletons. So this is a project with NSF, literally trying to make a soft exoskeleton to replace those rigid ones that you saw in some of my earlier slides. This is an exoskeleton that has 2 parts to it, an interior part that has sensors built into it so that you can know something about upper body movements of the shoulder, And then a second layer, which has several of these SMA actuators bridging the gap between your chest and your upper arm, which again, when activated, can create a pulling motion, which can support add and abduction motions with your upper body, entirely with soft form factors. And we also do a lot of work with those knitted textiles. I haven't talked as much about the knits, but we do a lot of work with them. This is an example of a compression garment, a gradated pressure garment, where the ankle is higher pressure than the mid calf, which is higher pressure than the upper calf. And it uses the knitted SMA material, which you see in black, paired with passive knitted material, which you see in yellow. And here's a video of us taking a heat gun to what this fabric looks like. And you can see by paneling them together, you can create two-dimensional contractions, which then when wrapped around the leg can produce compression in an entirely knitted robotic sock. And you can get really elaborate with the design process here. This is where having expertise in apparel design gets really fun, because you can piece together the different knit styles and fabric patterns to create really complex garments that can create differential motions depending on the geometry and the circumference and the performance requirement at different locations along the leg. So here's an entirely knitted SMA garment. You see the little motion trackers placed on it, which when heated can create a perfectly 3D customized contraction around the leg. And this is, again, you can make literally perfectly customized garments that can accommodate your precise anthropometrics in ways that a passive fabric could never even come close to. And we've got ongoing work here. We're halfway through a study actually looking at making compression garments, full-on lower body pants or even lower body socks with these knitted fabrics built into it to create medical quality compression, both for terrestrial use cases for folks with diabetes, lymphedema, but also for astronauts. Going back to my roots in the aerospace world to create useful compression on the lower body for folks as they're weightless. So just to wrap up, a couple of other areas that are interesting and that we are going to start working towards but haven't yet. Tourniquets, right? I started off by explaining that the most simple structure here is a tourniquet, using actuators to tension a passive fabric. Well, a student in our lab built a closed loop tourniquet based on this concept and won a design award at a recent Shape Memory conference. So there's an example of what the tourniquet looks like, but it includes closed loop PID control to actually create and sustain precise pressures that you would want, in this case, as a medical intervention to prevent you from bleeding out. But now imagine building these structures into the clothing that soldiers wear in the field. Now they experience a catastrophic injury, they lose a limb in combat. You don't want to have to wait for a medic or wait for your partner to come and tourniquet you so that you don't bleed out. What if your clothing can just do it automatically? You can do that with this type of technology, and the actuators themselves are nearly structurally invisible. So it doesn't get in the way of the clothing doing its job the rest of the time when you don't need the robotic intervention. The same thing could be true for the design of orthotics or prosthetics or braces, right? We create structures where the loading profiles and the forces and the torques can be modified over time. So what if that means you can now if you break a bone, you don't need a giant rigid plaster cast, which has to be cut off and reapplied to progressively heal the skeletal problem. What if we now make soft braces, which can be selectively rigid and whose rigidity can be modified with time? You can do that with soft robotic systems built into these structures. And then finally, I mean, there's a million other ways to take it. There's more work in the spacesuit area. There's the idea of making dynamic shapewear, not for any functional reason other than giving you a better silhouette. But you can make that silhouette change, you can make it loosen, you can make it tighten. That would be kind of a dream to a lot of people, the billion-dollar industry of shapewear. You can think about more exoskeletons. You can imagine making garments whose aerodynamic properties change, like skiers, so that you get lift when you want it, you get drag when you want it. Really cool things that are possible when you have textiles that are no longer just passive things. And the last thing I'll show off, the thing on the left, some of you may recognize this, that's me wearing a robotic jacket that we built in our lab, which is a functional replica of the Hollywood jacket worn in Back to the Future. And in Back to the Future, for those of you that seen it, Marty McFly travels to the future, quote unquote, which is 2015 according to the movie standards. So we are now 6 years beyond the future according to Hollywood. And one of the things in the movie that they experience in the future of 2015 are clothing that can auto-tailor. So he transports to the future, his jacket's too big, he pushes a button and it shrinks down to fit him perfectly. Well, in the movie, they did that by cheating. They had people with pulleys off screen yanking on ropes, which created a mechanical response in the jacket that he wore on screen. Well, we can do it for real. So this is a jacket that uses those actuators built inside of it, and that's me wearing it right when I started here at the U in 2015, proving that we can actually realize the future that Back to the Future promised us today with real actuators that can be built into clothing to give those effects and that don't have to be Hollywood magic. So that's the end of my talk. I know I went a little bit long. I appreciate everybody sticking around. I'm happy to answer questions now. You can shoot me emails later. Check out our website, but thanks for listening. And I can do questions now, or if people want to get out of here, I understand.
So thank you, Brad, for this very, very exciting sun costume talk. So any questions?
I guess I have one question. Thanks for the talk, by the way, it was really cool. When it comes to the joint problem that you described at first, was the ultimate solution to have the more wire-based textiles instead of the belt type mechanism? Was that the solution, or is that still a challenge now?
Sorry, so just make sure I understand your question. So the joint question for the spacesuit, is that what you mean?
Yeah. I guess spacesuit, and in general, it seems like the elbows and knees would be really tough places to, especially places where you need that kind of mobility. So I guess the solution for that.
Yeah, it's a really good question. It's an ongoing problem. Some of the really exciting work in the space of trying to understand how to make garments that are both stiff but flexible in the ways that you need them to be flexible actually is ongoing with being informed by maps of skin strain. So one of the really cool things that you can do now with modern digital image correlation systems is you can map out strain fields. The traditional way of doing it is in rigid materials, like you put a bar of aluminum in a tensile tester and you see how it deforms when you pull on it. You can do that with skin also. And think about skin. Skin is a really exotic material if you want to be morbid about it, right? It's a really interesting mechanical structure. And it already knows how to deform so that you can move, right? You are able to move because your skin allows deformations that don't get in the way of motion. So some of the really exciting work that's going on right now is trying to understand and map out what skin deformation looks like around the joints. Where is strain concentrating? Where is the skin stretching? Where is it compressing? And what are the orientations of those axes of stretch and strain, with the end goal ultimately of wanting to design textiles that mimic those axes of stiffness versus flexibility. And so the goal being, if you can, to engineer directional flexibility in the axes that require extension during motion, and then carry the stiffness in the perpendicular axis, with the hope that you can sustain a tight fit or a medical squeeze, but so that the axes of those loadings, the stiffness direction, is not directly being expanded. You aren't working against it. You aren't trying to impose strain in the direction of loading. And the way the best practice that's going on now, our lab's doing it and a bunch of other labs are also working on it, is to inform the design of the garments based on the natural strain patterns of human skin.
Awesome. Thank you so much.
Yeah, good question.
Other questions? So I have one. So Brad, where do you see the toughest problems being in the hardware, software, in the combination, in materials?
Yeah, it's a great question. I think the biggest areas for innovation in the space are at the material level. And the reason for that is because these actuators are only actuators because of quirky material properties, right? SMAs are only actuators. There's nothing special about nickel titanium as an alloy, other than the fact that when you put those two metals together, you get this really weird phase transformation behavior. And it's just a quirk of the chemistry that causes that to happen. And so they're useful because that alloy gives you that property, but then you're sort of stuck with that alloy if you want that property. And so there's a lot of really great work that's happening in material science departments of all places to try to adjust these alloys so that you get the reaction, the controllability that you want, but to tweak and improve the performance characteristics, right? We would love for these actuators to produce larger forces, or to cycle more times before they degrade, or to require a smaller temperature band to produce the stiffening effect. And all of those things, you're sort of at the mercy of what the material chemistry demands of you. And so, if I could snap my fingers and have a new degree and some new expertise to really innovate in this field, it would be material science. To work at that level of actually doping in different elements, different heat treatment and sort of mechanical working processes to optimize the performance of them at the one-dimensional level. And when you get better outcomes there, then the 2D and the 3D and the system level questions get a lot easier. Like when we work with the SMAs, the hardest problem that we have to solve in any system design is how much power is it going to take and how hot does it have to get in order to give us the mechanics that we want. And we're usually always wanting more. Like we would want a material that doesn't need to get as hot or doesn't need to eat as much power. And those are the limitations that we struggle with. So improving at the material level will make the engineering of the systems that come downstream way easier.
Okay. So
I have a question.
yeah.
Of course, it's probably very dependent upon what we just said, or an extension of it. Are there any groups that are trying to do wearables like the compression sleeves, where maybe you start with it cool down, and then once a person puts it on, the whole natural heat of the body will cause a slight compression?
Yeah, it's, if I didn't know better, I would say that I paid you to ask that question, because that is literally what we're doing right now in our lab. One of the implications to that answer I gave to the previous question is that the material alloy sets a lot of these performance requirements. And so nickel titanium is not the only one that can do this shape transformation. There are others which include other elements, or maybe include nickel titanium in a third element. And by doing that, it shifts the transformation temperatures wildly. There are some that activate cryogenically. There are some that activate in superheated scenarios. And there are some where the transformation behavior is right around or encompasses room and body temperature. And so that is a really exciting direction that we're working in right now, because it gives you exactly what you described. Maybe the garment has to start out in your freezer so that it's, quote, cold enough to be below transformation. But then you pull it out, you get it on your body, and in the 30 seconds or a minute it takes to acclimate to the environment or acclimate to, skin temperature, that heat from the reservoir that is you or that is the environment can be the power source that creates the phase transformation. And we've started working on that, and it's really promising. It's not without its own challenges, but that gets away from some of the biggest questions about needing big power supplies or having to deal with unwanted amounts of generated heat. If your body is the battery and the heat is just the heat of your skin, those problems go away. And that leads to really exciting, effectively unpowered robotics, because there is no external power source needed. The heat that drives these things is ambient. And so nothing additional is needed. The one downside to those architectures is that typically they're not controllable after the fact, right? If you have them on you and you're getting them heated because they're touching you, or you're heating them because the environment is supplying the heat, then you can't turn them off or you can't dial them up or dial them down because they're saturated already. And so you get effectively a one-time reaction, right? You get it loose or you get it limp right when it comes out of the freezer. It quickly acclimates and then transforms. And then when it equilibrates to that temperature, it is what it is. And so if you can imagine some architectures where that's really useful, like if you only need a one-time effect, and then that effect is maintained as long as it's in the ambient state, that's what you can get out of those scenarios. You wouldn't necessarily be able to get dynamic control of it after it's equilibrated, because it's basically fully actuated. So there's nothing more for it to give, even if you did then give it extra power or extra heat. So it's a really exciting way of thinking about kind of single-use robotics, but single-use robotics that require no power, which is a really unusual but high potential paradigm.
Thank you.
I think it would be easy to get around that just by like taking a cold shower for a second.
I mean, you could take an ice pack out and set it on the garment, and then set it back down and then get another effect. Whether you call that robotic or not is probably a philosophical debate. But yeah, I mean, there are ways to bring the temperature back down if you needed to, or you just put a zipper in it and you unzip it and take it off. Like you could do it that way.
Any other question? Thank you very much, and have a great weekend.
Yep. Thanks, Nikos.
Thank you, Brad.
Yep. See you, everyone.
Bye.